Students, I'm here to talk to you today about physical properties and physical changes. Physical properties are items that you can recognize with your natural senses. There's many different examples of physical properties, and we'll try to list most of them today. But we separate them into two categories. The first category is size dependent. By size dependent, we're talking about, well, if you change the size of an object, you're going to change the property. For example, if we were to take this rock, we could measure its volume, how much space it takes up. We might do that by using a ruler to measure each dimension, but that might take a lot of work. It might be easier to have a super huge beaker and then fill it up with water, immerse the rock in, like many of you have done with other objects, and measure how high the water rises. That helps us find the volume, or how much space the rock takes up. Another way we can measure it is by finding the mass. Coming over to our scales, we simply put the rock down, and we slowly are able to adjust our scales to find out just how much stuff is in our rock. Now it appears I didn't put quite enough weight on it. So all we have to do is just take a little more mass, add the mass to our scales. Oh, actually I think I did it wrong. My apologies. Let's take just a little bit off. And we can tell that we're pretty close to the right mass. Now, another size-dependent item is weight itself. Weight is different from mass, and you know this already, because mass is the amount of matter in an object, where weight is the force of gravity. And so we can simply find the weight by placing the rock on the scale. These are the only three items that depend on the size of the rock. Other properties that don't depend on size are items like color. This particular rock has a very unique name. We're going to talk about it when we talk about geology, but you can tell that the rock is green, and that gives it part of its name. In addition, we can smell the rock. Odor is a physical property. Now, to me, the rock doesn't really smell like anything. I have had some students in the past who seem to be a little bit addicted to smelling rocks. Kind of strange. Unique students, but we love all our students. Another physical property is just how hard the rock is. And that means, can we scratch the rock or not? And with my fingernail, I can't. We might be able to get other tools out. And I'm sure I have some back in the classroom that I could use that would actually scratch this rock. We could also taste the rock. Taste is another physical property, but I don't think I'm going to taste the rock today. All right, now here is a list of all of the non-size dependent features or properties of matter. Now, I might have missed a few. There are some that we're very familiar with, like color, taste, and odor. We've already talked about those. State of matter, whether it's a gas, a liquid, a solid, or a plasma. Changes of states of matter are a physical change. There's melting point, boiling point, and density. Now, a lot of kids get confused on density, but if I have a piece of chalk and I break it in half, I have changed the size of that chalk, but I have not changed the density of it. There are other physical properties that students aren't so familiar with, like malleability. Malleability is whether or not something can be pounded into a flat sheet. Typically, we're going to talk about metals when we talk malleability, and we are going to watch a video in class about that. There's brittleness, how easily something breaks. Chalk is very brittle, granite not so much. Ductility, whether or not something can be stretched into a wire. Conductivity, about physical changes, that simply means we're changing any one of the physical properties, or more than one of the physical properties, of the substance we're talking about. For example, if we have a nice piece of green paper, we can take the paper, draw on it, and have the color change. We can take the same paper, we can change its size by ripping it in half. Well, not quite half, but we ripped it. We can also do other changes. For example, we can do something called a chemical change, and most chemical changes also cause physical changes. Now, I'm not going to let this burn until it gets down to my hands, guys. I'm just not that crazy. But you can see that while we're having a chemical change, we are definitely having physical changes occur as well. We're changing the size, we're changing the mass, we're changing the color, we're definitely changing the odor as well. I'm not going to take it either. Just not going to happen. Now, I know in science, everyone loves science because of all the different categories we have to put different things in. Okay, so maybe everyone doesn't love science because of that. However, as scientists, we do try to classify things and put things into different groups and try to understand the differences of those. When we look at matter, we classify it often by its chemical properties and its physical properties. Now, I'm just going to talk about the physical properties today. So the chart you see behind me, we're only going to pay attention to this side of the chart. We start out with matter. Matter is anything that has mass and takes up space. Well, all matter can become mixtures as we start putting different parts of matter together. Matter that either acts or looks or is made up of different items, we start creating something known as a mixture. It's fairly simple. However, mixtures can be classified into two groups. One is a heterogeneous mixture. This is a mixture that looks uneven. You can tell the different parts. It's like if you take a bunch of dry beans and some peas and mix them together. You can easily point out the dried peas compared to the dry beans. Maybe we'll try that in a little bit. Also, we can turn a mixture into a homogeneous mixture, the one on the very bottom. A homogeneous mixture looks even throughout. It's like when you take sugar and salt and mix the two together. Just by looking at it, you're not going to see much difference because the sugar crystals and the salt crystals look so much alike. Now, both heterogeneous mixtures and homogeneous mixtures can be added to liquids, or they can be liquids themselves. When it's a heterogeneous mixture and it's turned into a liquid, we call it a suspension. Mud is a heterogeneous mixture. I don't know how many of you have sat down by a pool of mud recently, but as a little kid, maybe 4 or 5 years old, you may have done it once or twice. I know when I had done it, I was able to notice that some parts of the mud were very clear and very liquidy, soupy, watery. Other parts of the mud was very clumpy. This is definitely a heterogeneous mixture because it's not mixed evenly, and you can tell there's different parts and different characteristics to the different parts. Now, if it's a homogeneous mixture, some people do pronounce it homogeneous, but a homogeneous mixture, if that's in a liquid, it's called a solution because you have something like a solvent added to a solute, and the two will mix so evenly you cannot tell where one begins and one ends, and they appear to have the exact same properties. Let's go check a few of these out now. Alright, here we are with our examples of heterogeneous mixtures and homogeneous mixtures. We're going to start off with the heterogeneous mixtures because we already have our beaker of beans. All we need to do is add some of our good old split peas to it, swirl it around a little bit. Maybe that doesn't work quite so well, so we take our spoon, swirl it around, and we can tell, yes, it's a mixture. However, this mixture is easy to tell that there's different parts to it. It's unevenly mixed. We could make it evenly mixed by grinding down the beans and the peas into tiny little pieces and then mix it in, and it might be a lot harder to tell. However, because we can so clearly see the beans versus the peas, it is a heterogeneous mixture. Now, if we want to make this heterogeneous mixture into a suspension, we just add a bit of water. And you can tell that our beans and peas just sink to the bottom of this. And so it's not the greatest of suspensions. It's definitely not what we call a colloid. A colloid is when we make a heterogeneous mixture where the particles will never settle to the bottom. I'll either try to create another demonstration or find a video for you guys to see in class to make this point a little more valid. However, let's go ahead and set this aside and work with our homogeneous mixture. If we go ahead and take a little sugar and pour into our beaker, and then we take some salt, salt, and add that to our beaker, swirl it around, give it a stir of the spoon, and guys, I don't know about you, but it's pretty hard to tell the difference between the sugar and the salt. That's why we call this a homogeneous mixture. It all looks the same. Can we turn this into a solution? You betcha. All we have to do is we add water. And the water is going to slowly dissolve both the sugar and the salt. And if we mix and mix and mix, that's going to happen more rapidly. The water is known as a solvent. That's because the water is doing this dissolving, whereas the sugar and salt are both called solutes because they're getting dissolved. Now, did the properties of our water change as the sugar and salt dissolved? You betcha. Did all of it dissolve yet? Not quite yet. I don't know if all of it will dissolve because it's becoming highly saturated. When we talk about saturation, ladies and gentlemen, this is a discussion of ratio. How much solvent there is compared to how much solute. Now, we started off with a lot of sugar and salt and not a lot of water. Because of that, it's going to be much harder to dissolve all the sugar and salt. We can see a lot of it on the bottom still. That's because the water can only dissolve so much. And so this sugar salt water becomes highly concentrated. We can look at other substances and see this pretty clearly as well. If we take an Erlenmeyer flask and open up a package of Kool-Aid, and I'm going to use the really cheap lemonade, and add in our powder mix, our lemonade quickly becomes dissolved. And this lemonade that I've just made, because it doesn't have any sugar, it's going to taste really nasty if we tasted it, is also known as a weak concentration because there just isn't very much. Quite frankly, most people enjoy adding a lot of the flavoring to the water to make it have a stronger taste. They like having a higher concentration. When you go to the grocery store and you buy a can of frozen orange juice, it typically reads on it 100% concentrate. That doesn't mean you have to think real hard about the orange juice. What it means is that the orange juice is pure. There's no water added to it. Now, guys, can we separate mixtures? You betcha. If we come back to our suspension of beans and peas, I can go ahead and take out one bean at a time and one pea at a time until we have all the water separated from all the beans separated from all the peas, and we now have all three items again. Can I separate out my lemonade? Might be a little bit harder, but you betcha we can. By using the process of evaporation, we can let all the water come out and be left with the lemonade. Will it look, well, like the dry powder we saw before? No. It'll probably be caked all on the glass and be crusty and kind of disgusting looking. But it will still be there, and we'll have been able to separate them out. How about our sugar, salt water? Can we separate that? Yeah, we can. We can go ahead and evaporate all the water out as well and be left with the sugar and salt in the beaker. And then by very careful inspection, going from grain of crystal to grain of crystal, we could then separate the sugar from the salt. Mixtures can always be separated out from each other. It's a key characteristic of them. Now, let's go ahead and start our class.